Bavaria, Federal Republic of Germany, April 1945. At a Wehrmacht vehicle repair depot near Munich, 3 German military technicians disassemble a captured American Continental R975 radial engine removed from an M4 Sherman medium tank. The facility, designated Repair Workshop 217, has processed hundreds of disabled armored vehicles since 1943. Primarily German Panzer III, Panzer IV, and Panther medium tanks. Senior mechanic Hans Müller, age 42, a Maybach engine specialist with 18 years experience in precision automotive engineering, removes the cylinder head assembly. Wehrmacht technical doctrine requires complete engine teardown at 800 kilometers for Maybach HL120 engines and 1,000 kilometers for later models. Müller expects standard wear patterns, scored cylinder walls, carbon accumulation on piston crowns, worn compression rings requiring replacement. The inspection reveals contrary evidence. Cylinder bore surfaces show minimal scoring. Piston crown carbon deposits measure within acceptable service limits. Compression ring wear falls below projected parameters for the documented operating hours. The maintenance log indicates 1,487 kilometers of operation without major mechanical intervention, including cross-country movement through Bavarian terrain during the German retreat from France. Müller records in the Technical Evaluation Report, American engine construction philosophy differs fundamentally from German precision engineering standards. Service intervals exceed Wehrmacht specifications by 60 to 80%. Recommend immediate study of design methodology. This discovery represents more than isolated mechanical curiosity. By April 1945, the German armored force faces catastrophic attrition not from enemy firepower alone, but from mechanical unreliability that immobilizes tanks faster than Allied guns destroy them. The Continental R975 engine embodies industrial philosophy that powered American mechanized warfare from 1940 to through 1945, producing 49,000 to 130 for Sherman tanks compared to Germany's 1,347 Tiger heavy tanks and approximately 6,000 Panther medium tanks over the identical period. If you appreciate fact-based analysis of World War II mechanical systems and industrial strategy, please like this video and subscribe to the channel. Leave a comment indicating your location and which aspects of wartime engineering history interest you most. Aberdeen Proving Ground, Maryland, United States, August 1940. The United States Army Ordnance Department confronts urgent requirements for reliable power plants in the developing M3 medium tank program, later designated M3 Lee. European military operations in France demonstrate that mechanized warfare demands sustained mechanical performance under extreme operational tempo. German Wehrmacht forces employ blitzkrieg doctrine, combining speed, maneuver, and logistical endurance. American tank development programs, underfunded throughout the 1930s due to defense budget constraints, lack purpose-built tank engines. The Continental R975 9-cylinder radial aircraft engine enters consideration. Continental Motors Corporation manufactured this power plant since 1936 for civilian training aircraft. including the Boeing Stearman PT-17 Kadett primary trainer. The engine delivers 400 horsepower at 2,400 revolutions per minute, weighs 238 kilograms, and demonstrates exceptional reliability in flight training operations where engine failure creates unacceptable safety risks for student pilots. William S. Knudsen, former president of General Motors Corporation and coordinator of the National Defense Advisory Commission, advocates immediate adoption. Declassified production planning documents from August 1940 record Knudsen's assessment. Development of purpose-designed tank engines requires 24 to 30 months from initial design to production readiness. Continental R975 adaptation to armored vehicle requirements can achieve production standards within 90 days. Continental Motors engineering teams in Detroit, Michigan, modify the aircraft engine for armored vehicle application. Engineers install enhanced air filtration systems capable of processing dust concentrations exceeding aircraft operational environments. Exhaust manifold routing changes accommodate tank engine compartment layout. Main bearing assemblies receive reinforcement to withstand vibration amplitudes substantially higher than aircraft. Installations. The complete adaptation process requires 11 weeks. Aberdeen Proving Ground conducts initial trials in November 1940. The M3 medium tank, equipped with Continental R975 power plant, completes 800-kilometer endurance testing across varied terrain including sand, mud, and rocky surfaces. Temperature testing validates operation from -30 degrees Celsius to +50 degrees Celsius. The engine averages 1,500 to 2,000 kilometers before first major inspection, compared to 800 to 1,000 kilometers typical of German Maybach tank engines in Wehrmacht service. Friedrichshafen, Germany, 1941. The Maybach Motorenbau GmbH manufacturing facility produces the HL1 to OT RM12 cylinder liquid-cooled engine for Panzer III and early Panzer for medium tanks. The installation delivers 300 horsepower from 11.9 liters displacement, representing German precision engineering standards established in luxury automotive manufacturing. Maybach production methodology emphasizes component precision. Individual pistons undergo dimensional matching to specific cylinders, maintaining clearances within 0.02 to 0.05 millimeters. Crankshaft assemblies receive manual dynamic balancing to minimize vibration. Valve train. Components undergo hand lapping to achieve optimal sealing. Each completed engine requires 180 man-hours assembly time and undergoes 12-hour break-in testing before shipment. This precision engineering creates operational vulnerabilities. North African Campaign after-action reports from 1940 to document HL1-O engine failures at 500 to 600 kilometers in desert conditions. Fine sand particles bypass air filtration systems, entering cylinder bores and scoring cylinder walls. Compression loss results in power degradation. Eastern Front operations in 1941-1940 to reveal cold start difficulties. Lubricating oil viscosity increases at temperatures below -20 degrees Celsius, creating excessive mechanical stress during engine cranking. Maybach HL120 overhaul procedures require specialized tools and trained technicians, consuming 48 to 60 hours labor time per engine. The Maybach HL-30P30 engine, introduced in 1943 for Panther and Tiger heavy tanks, amplifies these challenges. The 23-liter 12-cylinder engine produces 700 horsepower, approximately 30 horsepower per liter displacement. The power plant contains 1,847 individual components requiring precision assembly. Cooling system capacity proves inadequate for sustained high-power operation. Carburetor assemblies suffer vibration damage. Transmission systems cannot reliably transfer the engine's torque output. Wehrmacht field reports from 1940 document systematic mechanical failure. The 11th Panzer Division operational summary from March 1940 records of 20 Panther medium tanks arriving at forward assembly areas. 7 experienced mechanical failures during road march. 4 additional vehicles failed after initial combat engagement. No vehicle completed for 100 kilometers without requiring major repair. Detroit, Michigan, United States, 1941. Continental Motors Corporation operates manufacturing facilities in 3-shift rotation, producing Continental R975 engines. For expanding tank production programs, Chief Engineer John Dorman establishes production philosophy fundamentally different from German precision manufacturing methodology. Declassified production manuals from 1941 document design specifications. Engine components must maintain functionality under adverse conditions, including inadequate maintenance, contaminated fuel supplies, and operation by personnel with minimal mechanical training. Continental deliberately incorporates design margins exceeding theoretical engineering requirements. Cylinder wall thickness exceeds minimum structural requirements by 15 to 20%. Piston-to-cylinder clearances measure 0.10 to 0.15 millimeters, substantially larger than German Maybach specifications of 0.02 to 0.05 millimeters. German engineers would classify such clearances as excessive, reducing theoretical compression efficiency and power output. American design philosophy prioritizes tolerance for contaminants. Wider clearances permit sand particles to pass through cylinder bores without causing piston seizure. Thermal expansion under high operating temperatures does not produce mechanical binding. Variations in lubricating oil viscosity do not prevent engine operation. The Continental R975 operates on aviation gasoline with octane ratings of 87, automotive fuel of 80 octane, or captured enemy fuel supplies. Power output decreases with lower octane ratings, but engine operation continues without mechanical damage. The 9-cylinder radial configuration provides operational redundancy. Each cylinder functions as independent unit. Single-cylinder failure reduces power output by approximately 11%, but engine continues operating on 8 cylinders. Field mechanics can replace damaged individual cylinders without complete engine disassembly to mechanics' complete single-cylinder replacement in approximately 4 hours using standard tools. Air cooling eliminates radiator systems vulnerable to combat damage. No coolant pumps, hoses, or antifreeze create failure points. For engine-driven fans force air through cylinder cooling fins. The lubrication system incorporates dual oil pumps. Primary pump failure activates backup pump. Automatically, dual-stage oil filtration and 30-liter oil capacity provide thermal buffering and contamination protection. Engine starting procedures require minimal preparation. Operators turn ignition key, engage electric starter, and achieve engine operation within 5 to 7 seconds at temperatures above -25 degrees Celsius. German Maybach engines require fuel priming, choke adjustment, oil circulation period, and in freezing conditions, external heating before starting. Production statistics from 1944 show Continental Motors manufacturing 2,000 engines monthly. Maybach Motorenbau produces 150 to 300 engines monthly at maximum capacity. Continental achieves this output with assembly time of 22 man-hours per engine compared to Maybach's 180 man-hours. Component standardization permits any piston or cylinder to fit any engine regardless of production date or manufacturing location. Maybach engines require batch-specific components matched to individual engine serial numbers. North Africa, November 1942. Operation Torch. The Allied amphibious landings in French North Africa introduces M4 Sherman tanks equipped with Continental R975 engines. To combat conditions in the Sahara Desert, ambient temperatures reach 50 degrees Celsius during daylight hours, dropping to 5 degrees Celsius at night. Airborne dust and sand particles create extreme challenges. For mechanical systems, British 8th Army experience with Crusader and Valentine tanks in 1940 to demonstrated vulnerability to desert conditions. Air filtration systems clog within hours of operation. Engine overheating causes mechanical failures. Fine abrasive dust scores cylinder walls, causing rapid compression loss. Captain James Lear, Maintenance Company Commander, 1st Armored Division, United States Army, records observations in November 1942. Third operational day in desert environment. Initial expectation predicted 50% engine failure rate. Actual results: 3 air filter. Cleaning operations required approximately 20 minutes per vehicle. All engines maintain operational status. Subsequent entry dated December 3, 1942. Battalion completed for 100-kilometer road march. 0 Sherman tank engine failures. British battalion operating parallel route abandoned 5 vehicles due to mechanical problems. The Continental R975 air filtration system employs 3-stage design. Primary cyclone separator uses centrifugal force to remove large particles. Secondary oil bath trap captures fine dust. Tertiary paper filter element provides final barrier. Maintenance procedure requires 15 minutes. Remove cover, drain oil bath, replace filter element. Reinstall. German Maybach filters require complete replacement rather than cleaning, and clog faster under identical conditions. Battle of Kasserine Pass, February 1943, represents first major American defeat against German Afrika Korps forces, commanded by General Feldmarschall Erwin Rommel. Tactical assessment confirms American units lacked combat experience, coordination, and effective leadership. Technical assessment reveals different conclusions. Of 48 Sherman tanks disabled during the engagement, 40 suffered combat damage from enemy fire. 6 experienced mechanical damage to transmission or track systems. 0 failed due to engine problems. By comparison, of 15 German tanks committed to battle, 3 experienced engine seizure from overheating during approach march to fail to start following overnight halt in cold conditions. Rommel's personal correspondence from February 1943 states, American forces demonstrate poor tactical performance, but their equipment impresses. Their tanks maintain operational capability consistently. Few things prove more challenging in warfare than an enemy whose machines do not fail. Tunisia Campaign Conclusion, May 1943, provides comprehensive data. Sherman tanks average 1,800 to 2,200 kilometers of operation in African theater conditions. German Maybach engines average 600 to 800 kilometers in identical environment. Wehrmacht technical intelligence teams transport captured Sherman tanks to Germany for detailed study. Engineering analysis reports document confusion. American Continental engine employs tolerances considered unacceptable by German precision engineering standards. Service life exceeds Maybach by factor of 2.0 to 2.5. Recommended revision of Wehrmacht production standards. The recommendation receives no implementation. German engineering doctrine maintains precision cannot be sacrificed for reliability. Eastern Front, December 1943 through March 1944. Wehrmacht armored formations operating in Soviet Union encounter winter conditions with temperatures ranging from -20 to -40 degrees Celsius. These environmental extremes expose fundamental weaknesses in German precision engineering. Philosophy: Maybach HL-30 engines in Panther and Tiger heavy tanks prove particularly vulnerable. Lubricating oil viscosity increases dramatically at low temperatures, say 30 weight oil, specified for normal operations. Becomes semi-solid below -15 degrees Celsius. Cold start procedures require external heating. Using portable torches, blow torches, or heated water circulation, each vehicle requires 40 to 60 minutes preparation before engine starting becomes possible. Liquid cooling systems create additional failure modes. Water glycol coolant mixtures freeze despite antifreeze additives. When concentrations prove inadequate, frozen coolant expands, cracking engine blocks, cylinder heads, and radiator cores. Coolant hoses become brittle, rupturing under pressure. Coolant pumps seize when residual water freezes in pump housings. Overnight, 116th Panzer Division maintenance reports from January 1940 for document typical results. Of 45 Panther tanks in division inventory, 18 remain non-operational due to cold weather mechanical failures. 12 require engine replacement due to cracked blocks from coolant freezing. 6 cannot start due to oil viscosity preventing crankshaft rotation. Continental R975 air-cooled engines demonstrate superior cold weather performance. Air cooling eliminates coolant freezing as failure mode. No radiators, hoses, or pumps can be damaged by ice formation. Recommended winter lubricant, say 1OW oil, maintains adequate viscosity to -30 degrees Celsius. Starting procedure remains identical to summer operations. Turn ignition key. Engage starter. Achieve engine operation within 7 seconds. American armored units receive winter preparation training and equipment modifications on scheduled basis. German forces improvise solutions using field-expedient methods with inconsistent results. Ardennes region, Belgium and Luxembourg, December 1944. Wehrmacht launches Operation Wacht am Rhein Watch on the Rhine, the final major German offensive on Western Front. 6th SS Panzer Army and 5th Panzer Army, totaling approximately 410,000 personnel, 1,400 armored vehicles, and 4,000 to 100 artillery pieces. Attack American positions in heavily forested terrain. Weather conditions create extreme mechanical stress. Temperatures drop to -20 degrees Celsius. Snow accumulation reaches 30 to 50 centimeters depth. Frozen ground and ice-covered roads challenge vehicle mobility. German planning anticipates mechanical challenges. Wehrmacht logistics units pre-position portable heating equipment for engine warming. Technical bulletins distribute revised cold start procedures. Lubricant supply increases to permit more frequent oil changes using appropriate viscosity grades. Reality diverges from planning. Morning of December 16, 1944, First Offensive Day. Approximately 1/3 of German armored vehicles fail to start. Maybach HL-230 engines in Panther and Tiger to heavy tanks prove particularly problematic. Oil viscosity prevents crankshaft rotation. Electric starters cannot overcome resistance. Mechanics employ portable torches to heat engine blocks, requiring 40 to 60 minutes per vehicle. Successful starts do not guarantee sustained operation. Cold engines experience accelerated wear during warm-up period. Thermal shock causes cracking in precision-machined components. SS Obersturmbannführer Joachim Peiper, Commander Kampfrupp Peiper, 1st SS Panzer Division. Reports of 70 to tanks and self-propelled guns assigned to Kampfrupp on December 16th. 18 cannot move due to engine starting failures. 9 additional vehicles experience mechanical breakdowns within first 3 hours of operation. Forward momentum lost before enemy contact. American forces face tactical surprise and initial disorganization. Mechanical systems perform reliably. Captain Charles McDonald, 2nd Infantry Division, United States Army, records, morning of December 16th, bitter cold conditions. Orders received, immediate withdrawal. German breakthrough in progress. Crew enters Sherman tank positioned outdoors overnight in -20-degree temperature. Driver activates ignition. Engine starts immediately on first attempt. This response considered normal. No alternative outcome anticipated. Continental R975 air-cooled design proves advantageous in extreme cold. No antifreeze to freeze. No coolant hoses to crack. No coolant pumps to seize. Standard winter lubricant, say 10W oil, maintains flowability. American forces prepare equipment for winter operations according to established schedules. German forces improvise with inconsistent effectiveness. After 1 week of combat, patterns emerge clearly. Each German panzer division loses 30 to 40% of armored vehicle strength to mechanical failures and fuel shortages, not enemy action. United States Fifth Army restores combat effectiveness rapidly. Disabled vehicles return to service after field repairs. Maintenance companies operate in forward areas despite weather conditions, replacing track assemblies, repairing armor damage, installing replacement Continental R975 cylinders. Colonel Clarence Beck, 3rd Army Maintenance Service Commander, reports, during coldest week of Ardennes operations, maintenance units repaired 140 Sherman tanks. In 95% of cases, problems involved track systems, suspension, or armor damage. 0 engine failures attributed to cold weather conditions. German offensive culminates in January 1945. Allied forces recover abandoned German armored vehicles throughout Ardennes region. Many show no combat damage. Technical intelligence inspection reports document engine and transmission failures from mechanical overload, cold weather stress, inadequate lubrication. Crews abandoned vehicles, withdrew on foot. Winter 1944 to 1945 validates fundamental principle. Wars are won not by sophisticated technology alone, but by reliable mechanical systems that function consistently under adverse conditions. Germany, March through April 1945. Allied forces advanced rapidly into German territory following successful Rhine River crossings. Operational tempo reaches unprecedented intensity. Armored formations advance dozens of kilometers daily. Static defensive positions give way to mobile warfare emphasizing speed, maneuver, and exploitation. This operational tempo creates mechanical stress patterns different from earlier combat. Track assemblies wear rapidly from sustained high-speed movement on paved roads. Suspension components experience fatigue damage from continuous operation. Transmissions overheat from constant gear changes and power demands. Engines endure sustained high-load operation. Lieutenant James Bates, Maintenance Platoon Commander, 9th Armored Division, United States Army, documents results. Past 3 weeks, Maintenance Platoon repaired 67 Sherman tanks, replaced approximately 140 individual track shoes, 20 to complete road wheel assemblies, 18 transmission units, engine-related repairs, 8 individual cylinder replacements due to shrapnel damage from near-miss artillery strikes, 0 complete engine failures from mechanical wear. Field repair operations occur near front-line positions, sometimes under artillery fire. Mechanical modularity of Continental R975 enables rapid repairs. Sergeant William O'Brien, 7th Armored Division, records Sherman tank number 27 sustained artillery fragment penetration of engine compartment. 2 cylinders damaged by shrapnel. Vehicle recovered to field maintenance position. To mechanics completed cylinder replacement in 3 hours. Refilled lubrication system. Restarted engine. Same tank returned to combat operations that evening. German forces cannot achieve equivalent repair capability. Maybach HL-30 engine with damaged cylinder typically requires complete engine removal. Factory-level rebuild facilities, specialized tools, and 1 week minimum time. Continental R975 modular design permits replacement of individual damaged cylinders without complete engine disassembly. American logistics doctrine positions spare parts with forward combat units. GNC trucks transport engine components including cylinders, pistons, bearings in standardized containers. Parts interchangeability across production batches and manufacturing plants enables any spare component to fit any engine. German logistics rely on centralized depot supply systems. Many depots already destroyed by Allied air attack or overrun by ground forces. Required spare parts do not reach forward units. Disabled vehicles remain stationary. April 1945, raw pocket encirclement. Approximately 130,000 German military personnel, 170 armored vehicles, hundreds of artillery pieces become trapped. Following capitulation, American technical intelligence teams inventory captured equipment. Report documents of 170 captured German armored vehicles, 112 abandoned due to mechanical malfunctions. Of mechanical failures, 89 involved engine or transmission problems not repairable under field conditions. 23 failures involved fuel exhaustion. Only 58 vehicles destroyed by direct enemy fire. Most abandoned vehicles remain 60 to 70% serviceable. Failed steering mechanism leads to vehicle abandonment. Cracked engine block prompts demolition by crew. Single missing specialized component results in roadside disposal. Sherman tanks continue combat operations despite severe damage. Vehicle with destroyed track assembly serves as static firing position. Engine powers electrical system. Turret rotation, weapon systems. Tank with penetrated hull armor remains mobile. Engine provides propulsion to maintenance facility. Vehicle with damaged transmission operates in lowest gear ratio, moving slowly but maintaining mobility. German Panther with comparable damage becomes immobilized metal structure. Technical Lieutenant Ernst Weber, 2nd Panzer Division, states, "We could not comprehend American capability. We observed Sherman tank penetrated by anti-tank round. Operating in combat next day, our tanks sustained minor mechanical fault, became permanent losses. We lost this war not only on battlefield, we lost in repair facilities." Pacific Theater, 1944 to 1945. United States Marine Corps conducts amphibious assault operations across Japanese-held islands, including Saipan, Peleliu, and Okinawa. Environmental conditions create challenges exceeding European and North African theaters. Relative humidity maintains 90 to 95% continuously. Ambient temperatures reach 40 degrees Celsius. Tropical vegetation, volcanic dust, and coral particulates create unique mechanical stresses. Japanese island environments cause rapid corrosion of ferrous metals. Electrical systems short-circuit from moisture infiltration. Lubricants emulsify when mixed with water vapor, losing protective properties. German Maybach engines never tested under such conditions. Japanese tank engines, primarily Mitsubishi Type 100 air-cooled diesels, theoretically possess better moisture tolerance, but consistently fail from water contamination in fuel systems. Continental R975 maintains operational capability. Sergeant Anthony Romano, mechanic, 4th Marine Division, recalls Saipan Island conditions caused rapid deterioration of all equipment. Personal weapons developed rust overnight. Clothing remained wet for weeks. Skin conditions from fungal infections proved common. Sherman tanks started every morning. Engine compartments showed condensation throughout. Water accumulated in every void space. Turn ignition key. Engine roars to life as usual. Design simplicity provides reliability advantage. Minimal electrical components reduce short-circuit vulnerabilities. Magneto-ignition system operates under waterproof rubber insulation. Air cooling eliminates liquid coolant to mix with moisture infiltration. Carburetor design, though primitive by engineering standards, proves robust. Peleliu Island, September 1944, represents one of Pacific theater's most intense battles. Ambient temperature exceeds 45 degrees Celsius. Coral limestone formations create dust finer than sand, infiltrating every mechanical system. Marine units operate M4 Sherman variants with General Motors 6.0 for 6 twin inline-6 diesel engines alongside M4A1 variants with Continental R975 gasoline engines. 1st Marine Division Technical Summary reports. Diesel-powered Sherman tanks demonstrated sensitivity to coral dust contamination. Fuel injection systems clogged. Fuel injectors failed, resulting in 12 engine failure incidents from blocked filters. Sherman tanks with Continental R975 gasoline engines. 3 filter-related maintenance actions. Cleared by filter cleaning requiring 15 to 20 minutes per vehicle. 0 complete engine failures. Okinawa Island, April through June 1945, final major Pacific theater battle. Sustained rainfall transforms terrain into mud. Armored vehicles sink to turret level. Tanks operate as recovery vehicles, towing disabled vehicles, working at maximum power output for sustained periods. Engines experience continuous high-load operation causing elevated temperatures. Lieutenant Colonel Robert Neiman, Tank Battalion Commander, reports lost more vehicles to terrain conditions than Japanese anti-tank weapons. Continuous recovery operations required maximum engine power. Engines overheated from sustained high-load operation. Continental R975 maintained. Functionality: 3 tanks operated 18 hours continuously pulling disabled vehicles from mud. 0 engine failures. Pacific Theater final statistics. 1945. Approximately 4,800 Sherman tanks deployed against Japanese forces. Lost to enemy fire, approximately 1,000 to 140 vehicles. Lost to accidents and non-combat causes, approximately 380 vehicles. Engine failure as cause of non-combat loss, 47 vehicles, approximately 12% of non-combat losses. Approximately 1% of total losses. Japanese Type 97 Kaiha medium tank statistics for comparison. Total losses approximately 2,100 vehicles. Combat losses approximately 680 vehicles. Technical failures approximately 890 vehicles. Approximately 40% of total losses. Tropical Pacific conditions validate Continental R975 universal applicability. Engine demonstrates reliability in European cold, North African desert heat, and Pacific tropical humidity. May 1945, Europe. World War II concludes with approximately 49,000 to 130 for M4 Sherman tanks produced. 40,000 remain in Allied inventory. United States transfers surplus armored vehicles to rebuilding European nations, including France. Belgium, Netherlands, Italy. Continental R975 engines continue service. Israel, 1948. War of Independence. Newly formed Israeli Defense Forces acquire military equipment from available sources. Initial armored vehicle purchases include Sherman tanks obtained from European surplus stocks classified as scrap metal. Vehicles average 5 to 6 years age. Stored outdoors without environmental protection. Menahan Regal, Haganah Mechanic, recalls, received 3 Sherman tanks from France. Vehicles participated in 1940 for combat operations, remained stored outdoors for 2 years. Assessment predicted complete mechanical overhaul required. Performed basic maintenance. Added lubricating oil. Cleaned air filters. Installed charged batteries. Engines started immediately. Could not believe functionality after extended storage. Israeli Defense Forces operate Sherman tanks until 1970s. Continental R975 engines receive upgrades including improved carburetors and air filtration systems. But fundamental design remains unchanged. France operates Sherman tanks through 1960s in First Indochina War, 1946-1954, and Algerian War 1954 to 1962. Same engines function in tropical Southeast Asian conditions and North African desert environments. South American nations, including Argentina, Chile, Paraguay, purchased Sherman tanks during 1950s. Some vehicles remain in service through 1980s, approximately 40 years after original manufacture. West Germany, 1952, forms Bundeswehr following NATO admission. United States transfers military equipment including Sherman tanks to newly established German military. German mechanics. Many former Wehrmacht personnel service Continental R975 engines. Oberfeldwebel Ernst Klein, former 21st Panzer Division mechanic, later Bundeswehr instructor, writes in 1950 for training manual. Continental engine design structurally simple. Does not meet traditional German precision engineering standards. This simplicity ensures exceptional reliability. German mechanics must abandon conventional expectations regarding tight tolerances. This engine operates according to different engineering logic. It functions effectively. Recognition arrives but cannot reverse historical outcomes. Continental Motors Corporation produces R975 engines through 1960s. Total production exceeds 54,000 units. Maybach HL to 3.0 total production approximately 9,000 units. Post-war Maybach attempts to resume engine manufacturing, but reputation for technical sophistication combined with operational unreliability persists. Continental R975 establishes legendary status, not for maximum power output or fuel efficiency, but for consistent operational capability under all conditions. Vietnam, 1965 to 1975. United States military forces deploy new generation armored vehicles including M48 Patton Main battle tank, M551 Sheridan light tank. Advanced technology includes complex power plants, electronic fire control systems, hydraulic transmission units. Results demonstrate catastrophic unreliability. M550-1 Sheridan's specifications appear impressive. Aluminum armor reducing vehicle weight. 152mm gun launcher capable of firing both conventional ammunition and guided missiles. Diesel-electric transmission. Combat performance proves disastrous. United States Army Vietnam Report, 1969. M551 Sheridan vehicles experience mechanical failures more frequently than successful weapon engagements. Transmission cannot endure tropical humidity and heat. Electronic systems short-circuit from condensation. Mean time between failures approximately 50 operating hours. Veteran mechanic who serviced Sherman tanks in 1945 and Sheridan tanks in 1968 summarizes. Lessons forgotten. Sherman design philosophy emphasized simplicity, resulted in minimal breakdowns. Sheridan design emphasizes complexity, results in constant failures. American engineering followed. German precision methodology achieved identical unsatisfactory results. M1 Abrams main battle tank, introduced 1980s, employs a GT 1500 gas turbine engine producing 1500 horsepower. Reliability improves compared to M551 Sheridan, but remains inferior to simple diesel engines. Fuel consumption approximately 400 liters per 100 kilometers. Continental R975 consumed approximately 200 liters per 100 kilometers, despite producing 1/4 the power output. A GT 1500 turbine engine maintenance requires specialized equipment not available in field conditions. Complete engine replacement requires 8 to 10 hours with 4-person maintenance team. Single Continental R975 cylinder replacement required 3 hours with 1 mechanic. Progress or repetition of historical errors? Russian Federation military operations. Ukraine, 2022 to 2024. Advanced T90M and T80 BVM main battle tanks frequently disabled by minor electronic malfunctions. Complex sighting systems fail from vibration stress. Field maintenance facilities without. Factory-level tooling cannot affect repairs. Older T64 and early T70 to tanks. Cruder design, but simpler construction sometimes demonstrates superior operational availability. History repeats patterns. Excessive complexity loses to functional simplicity. Pursuit of perfection loses to practical reliability. Fundamental question: why did German engineering superiority fail to produce military victory? Answer lies not in technical specifications, but in philosophical approach to mechanical design. Germany, 1930s. Nation of precision engineering, advanced chemistry, optical manufacturing. Traditions of Karl Benz, Rudolf Diesel, Robert Bosch. Every manufactured product treated as artwork requiring perfection. Leica cameras. Carl Zeiss optics. Mercedes-Benz automobiles represent engineering excellence. Engineers trained in precision. Culture. Component must achieve ideal specifications. Clearances minimal. Efficiency maximal. Compromise equals failure. Ferdinand Porsche, Tiger tank designer, stated, "If machine lacks technical perfection, it possesses no right to exist." Philosophy produced masterpieces suitable for peacetime conditions, unsuitable for warfare. Maybach HL-30 engine designed as pinnacle of engine manufacturing art. 700 horsepower from 23 liters displacement equals approximately 30 horsepower per liter. Impressive for 1940 to technology. Cost of perfection. Complexity. Engine contained 1,847 individual components requiring interaction within tolerances of 0.02 to 0.05 millimeters. Any deviation caused system imbalance. German designers believed correct execution guaranteed long service life. No safety margins incorporated. Design assumed tanks would not operate continuously at maximum power. Filters would not clog with dust. Oil changes would occur on schedule. United States, 1930s. Nation of mass production. Traditions of Henry Ford. Wright brothers. Priority. Functionality of complete system rather than perfection of individual components. American engineer perspective. Product must function in hands of inexperienced user under worst conditions with minimal maintenance. Ford Model T designed for farmer without mechanical training. Village blacksmith with basic tools must accomplish repairs. Logic transferred directly to Continental R975. Wider clearances. Because tank operations include dust contamination. Complete parts interchangeability. Because field conditions prevent precision fitting. Modular design. Because mechanics might lack advanced training. Continental engineer John Dorman wrote in 1940 one internal memorandum. We manufacture engine for warfare, not showroom display. Must survive everything soldiers will do to it, including soldiers who never read instruction manuals. Two philosophies collided on European battlefields 1944 to 1945. German tank crew received Panther tank with 88-page engine operation manual, including warm-up procedures, oil viscosity tables for temperature ranges, detailed starting sequences. American tank crew received Sherman tank with 12-page manual. Essential content. Turn ignition key. Drive vehicle. If malfunction occurs, summon mechanic. Results predictable. German crews damaged precision machines through imperfect operation. Insufficient warm-up caused block warping. High RPM cross-country operation caused premature transmission wear. Delayed oil changes caused cylinder scoring. American crews treated Sherman as agricultural tractor. No special procedures. No rituals. Engines endured abuse. Training statistics confirm contrast. German Panzer Training Center, Bergen. 1943. 8 weeks total instruction including 2 weeks technical training on Maybach engines. Emphasizing starting procedures. Shutdown protocols. United States, Fort Knox. 1943. 6 weeks total instruction including 3 days basic technical instruction covering fueling procedures, starting procedure, when to request maintenance support. Germans trained specialists, Americans trained operators. Mass warfare favored operator training. General Oberst Heinz Guderian, Inspector General of Panzer Troops, reported to Adolf Hitler. March 1944. German equipment technically superior to enemy equipment. We use armored vehicles faster than production replaces them. Problem not design quality. Problem reliability and maintainability. Hitler ignored recommendation, demanded increased production of Tiger and Panther tanks. Increased armor thickness, larger caliber weapons. No one demanded simplicity. Wars won by simple machines functioning consistently, not sophisticated machines failing frequently. Post-war period. Allied forces gain access to German government archives including Reichsministerium für Bewaffnung, Unmunition Reich Ministry of Armament and Munitions documentation, Wehrmacht armored unit summaries, statistics more severe than wartime intelligence indicated. United States Technical Intelligence Report, November 1945, based on captured German documents. Maybach HL to 30P30 engine Panther and Tiger tanks. Average overhaul interval in controlled test conditions, 800 to 1,000 kilometers. Actual field service life, 600 to 750 kilometers. Severe conditions desert, extreme cold, cross-country, 400 to 500 kilometers. Failure rate before 500 kilometers, approximately 23%. Average engine replacement time in field conditions, 48 to 72 hours. Specialized tools required, 17 items. Personnel required, 4 to 6 trained mechanics. Maybach HL-120 TRM engine Panzer III and early Panzer for tanks. Average service life, 900 to 1,000 to 100 kilometers. Field service life, 700 to 900 kilometers. Failure rate before 500 kilometers, approximately 15%. Engine replacement time, 36 to 48 hours. Specialized tools required, 12 items. Personnel required, 32 for trained mechanics. Continental R975EC to Engine M for Sherman tank. Overhaul interval in factory testing, 1,800 to 2,000 to 100 kilometers. Field service life, 1,500 to 1,900 kilometers. Severe conditions, 1,000 to 100 to 1,500 kilometers. Failure rate before 1,000 kilometers, approximately 4%. Complete engine replacement time, 10 to 14 hours. Single cylinder replacement time, 3 to 4 hours. Specialized tools required, none. Standard mechanics toolkit sufficient. Personnel required for complete engine replacement, 2 to 3 mechanics. Personnel required for single cylinder replacement, 1 to 2 mechanics. Most significant statistics concern spare parts availability. Oberkommando der Heers German Army High Command document, January 1945. As of January 15, 1945, German armored vehicles in repair status or awaiting spare parts, Panther, 847 units, of which 623 await engines or transmissions. Tiger 1 and 2, 142 units, of which 89 await engines. Panzer 4, 456 units, of which 298 await engine components. Average waiting time for engine parts, 18 to 35 days. Tanks destroyed by own crews in December 1944 due to impossibility of repair, 412 vehicles. Comparison, United States First Army Maintenance Report, January 1945. Average waiting time for Sherman spare parts, 2 to 4 days. Tanks classified as irreparable due to engine damage. In December 1944, 7 vehicles, Percentage of tanks returned to service following engine repair: 94%. Economic analysis equally revealing. Production cost: Maybach HL-30, approximately 18,000 Reichsmarks, equivalent to $7,100 in 1940 for values. Production cost: Continental R975, approximately $1,850. Labor requirements: HL-30, approximately 180 man-hours. Labor requirements: R975, approximately 22 man-hours. Time required to produce one Maybach HL-30 permits Continental. Motors to produce approximately 8 Continental R975 engines. Cost of one Maybach HL-30 purchases: approximately for Continental R975 engines. Most significant measurement: kilometers actually driven by tank before irretrievable loss. British Tank Technology Commission Study, 1946. Average distance from factory delivery to irretrievable loss for German armored vehicles. Tiger I, approximately 680 kilometers. Tiger II, approximately 490 kilometers. Panther, approximately 750 kilometers. Panzer IV, approximately 920 kilometers. Average distance for M4 Sherman, approximately 1,640 kilometers. German tanks lost due to technical causes or abandoned, approximately 60 to 65% of total losses. M4 Sherman lost to enemy fire, approximately 80% of total losses. German tank drove to its destruction. American tank drove to victory. Continental R975 story transcends mechanical engineering, represents industrial philosophy determining warfare outcome. Lesson applicable beyond World War to context. 1960s Vietnam War. United States employs M48 Patton tank, M551 Sheridan light tank. Complex power plants, electronic fire control, hydraulic transmissions, catastrophic unreliability. M551 Sheridan, aluminum armor, 152 mm gun launcher, missile capability, diesel-electric transmission, technological marvel specifications, maintenance nightmare reality. Vietnam Operations Report, 1969. Sheridan vehicles fail mechanically more frequently than successful combat engagement. Transmission cannot endure jungle humidity. Electronics short from moisture. Mean time between failures, 50 hours. Veteran mechanic, Sherman experience 1945. Sheridan experience 1968. Lessons forgotten. Sherman simple, rarely failed. Sheridan complex, constantly fails. American engineering followed German precision path, achieved German results. 1980s M1 Abrams main battle tank, AGT-1500 gas turbine, 1,500 horsepower. JET engine technology in armored vehicle. Reliability superior to Sheridan, inferior to simple diesels. Fuel consumption, 400 liters per 100 kilometers. Continental R975 consumed to 100 liters per 100 kilometers at 1/4 the power. Turbine maintenance requires specialized equipment. Engine replacement, 8 to 10 hours, 4-person team. Single R975 cylinder, 3 hours, 1 mechanic. Progress or historical repetition? Russia-Ukraine conflict 2022 to 2024. Advanced T-90M, T-80BVM main battle tanks disabled by electronic failures. Complex sighting systems fail from vibration. Field maintenance facilities cannot repair without factory equipment. Older T-6 for T-70 to tanks. Cruder but simpler. Sometimes demonstrates superior operational availability. History repeats. Complexity loses to simplicity. Perfection loses to reliability. Continental R975 remains operational in museums, private collections, reenactment groups. After 80 years, proper fuel and oil enable engine start. Some machines transcend time. Function persists. History written not only by political leaders, military commanders. History created by engineers drawing blueprints. Factory workers assembling components. Mechanics repairing equipment in Arctic cold and tropical heat. Continental R975 never achieved. Highest power output of World War II engines. Not most fuel efficient. Not most elegant design. On paper, German Maybach surpassed in nearly every specification except one critical measurement: reliability. Reliability not measured in horsepower ratings, measured in kilometers to victory. Ours mechanics do not spend on repairs. Lives of soldiers who do not die inside disabled vehicle under enemy fire. German mechanics in Bavaria, April 1945, could not comprehend American engine running 1,500 kilometers without major overhaul. They understood world through precision, efficiency, perfect engineering. But warfare is not mathematics problem. Warfare is chaos, dust, mud, extreme temperatures, mechanical overload, impact damage, vibration. Inexperienced mechanic who never read manual. Soldier adding incorrect lubricant because proper supply unavailable. In that chaos, winner not perfection, winner, machine that does not stop. Americans understood earlier, did not create masterpiece, built tool, crude, loud, inefficient, but tenacious. Continental R975 became Sherman tank's heart. Sherman became symbol of industrial power, not for armor protection or firepower, but because it operated when needed, drove, fought, returned. Statistics conclusive. 49,000 to 130 for Shermans produced. Approximately 8,000 combat losses. Fewer than 100 losses from engine failure. Germany built 6,000 Panthers. More than half lost to technical problems. Unrepairable in field. Wars not won by tanks as such. Wars won by tanks that move. Nearly 80 years passed. Continental R975 lessons remain valid. Modern fascination with complexity, electronics, artificial intelligence, autonomous systems. Design machines requiring specialized technicians. Yet warfare winner remains. Machine functioning. When specialist absent, when spare parts never arrive. When reality differs from manual specifications. Spring 1945, German mechanics disassembling Continental R975. Incomprehension. How can something so simple function? Where is precision? Where is sophistication? They searched wrong location. Sophistication not in components. Sophistication in philosophy. Best component is component that does not fail. Best engine is engine not requiring genius for service. Continental R975 did not defeat Maybach HL to 3.0 through superior technology. 1 through superior concept. Lesson worth remembering in world where complexity often becomes objective rather than means. Sometimes best solution not most elegant. Often victor not fastest sprinter, but finisher who reaches destination. Continental R975 reached destination. Thundered, smoked, roared. Reached from African deserts to Ardennes forests. From Pacific jungles to Berlin streets. When final Sherman halted beside Reichstag. May 1945, engines still running. Not prettiest engineering triumph, but victory nonetheless.